Today, we're going to learn how to design a shaft. Now, generally, shafts are complex structures. They can include things like gears. They can have multiple changes in diameters, meaning different types of shoulders. They can have pins, splines, and keys that allow us to transmit torque from one shaft to another. Ultimately, in designing shafts, we have to consider the critical locations, the locations within the structure where we expect stresses to be highest. These are the locations where we need to evaluate things. We need to determine the static failure of these structures and the fatigue failure of these structures. Now, critical locations are usually located on the outer surface. It can be where our bending moments are largest. Can also be where torque is present, where we're actually applying that torsional shear stress. It is often places where stress concentrations exist, where we have shoulders that are either sharp or chamfered, as well as it can be locations where we transition from one shaft and transmit torque into another shaft, meaning places where there's keys, pins, and splines. Now, the stresses in shafts, what are they? Generally, they are bending stresses, torsional shear stresses, and axial normal stresses that are applied to a shaft. And these can be presented as either mean stresses, but also as alternating components of stress. So they can be constant, but they can also be fatigue loading from a max to a min. Now, generally, the axial stresses, the thrust stresses that are going along the axes of the shaft are constant. They are also relatively small to the bending moment stresses. And so for brevity, we will not consider the axial stresses. But in real shaft designs, they are important and they should be included. It's just the equations get a little bit complicated, right? So now let's start with the case of a shaft that has a normal bending moment stress and torsional shear stresses. Let's get those general shaft equations. And let's also consider this as a case of fatigue. In this case, we will have both potentially a normal stress amplitude and a mean normal stress amplitude, as well as a shear stress amplitude and a mean stress amplitude, meaning both the normal stresses are alternating and have a mean value, and the shear stresses are alternating and have a mean value. Now, considering that we have a shaft and we might have changes in the diameter, we also have stress concentration factors as we go from a big diameter to a little diameter potentially across the shaft. Now, for round shafts, where we know the equation for the polar moment of inertia and the second moment of inertia, we can derive a more specific form of these equations as follows. Where now the normal stress amplitude and the mean stress amplitude and the shear stress amplitude and the mean shear stress amplitude are in terms of the diameter of our shafts, right? But that we also have the bending moments, and we have the torque that is applied, both the amplitude and the mean values for our geometry. And let's note that D in these equations are the shaft diameter. So now we've got these stresses. We've got the mean, we got the amplitude, both normal and shear. How do we then determine the failure? How do we take this state of stress and transform it so that we can determine the potential fatigue or static failure of our shafts? Well, of course, we're going to need to choose a failure criterion. One of the best, the most accurate, is the distortion energy theory, which is the von Mises stress. In this case, let's think about a shaft that's loaded with no axial load, meaning we simply have normal bending stresses, and we have torsional shear stresses. In that case, for that state of stress, the von Mises stress simplifies to the following form. But also, if we have fatigue loading, we can find von Mises stress in terms of the stress amplitude in our structure, but also in terms of the mean stress, the average stress of a cycle within our structure. So now we have these parameters that represent the full state of stress as a single scalar value for the different types of fatigue stresses we expect in our geometry. So now, with these single valued stresses in terms of fatigue, we can finally start to evaluate if fatigue failure will occur. Now, an endurance limit. Of course, we need a property. We need a property to compare with to know if we have finite or infinite life. The first step, determine the rotating bending endurance limit. The endurance limit if we are fully reversed fatigue cycling. The second thing for us to do is to find the actual endurance limit of our structure, to include things like the load factor, surface factor, temperature factor, reliability, and miscellaneous factors to find the actual endurance limit, the stress amplitude below which our structure should have infinite life. Now that we have the real endurance limit of our structure, we can then go and apply our fatigue failure criterion. Now, our structure could have mean stress. We could have a case where we're pulsating in tension or compression. And so we need to use one of our fatigue failure criterions to help us to determine a fully reversed stress amplitude at which we can calculate the cycles to failure. The classic approach, the classic equation is Goodman's equation, where the stress amplitude of our body divided by its actual endurance limit plus the mean stress applied to our body divided by our ultimate tensile strength is equal to 1 over the safety factor in our design. Inputting the von Mises stress for these values of stress amplitude and mean stress, we end up with this fairly complex form of equation where we include not only the safety factor, but the actual diameter of our shaft, the fatigue stress concentration factors, both axial and shear, and the moments and the torque, both in terms of amplitude and mean stresses. It's a lot going on. But with this equation, we can then rearrange and solve to find the optimal diameter of our shaft, the required diameter, in order to meet our safety factor based on the moments and torque that's actually applied to our structure. And we can then use this to solve for the diameter, which is going to give us infinite life. A shaft that will survive unlimited number of cycles by having the right diameter for the boundary conditions applied to it. Now, of course, this is just one fatigue failure criterion, the Goodman diagram, but there are many of them. We went over, I think, about 6 of them in previous videos. So how do we apply this approach to others? Well, what we can do is we can introduce modular stresses, a stress A and a stress B, where A is relative to the amplitude and B is relative to the mean value of stresses within our structure. With these modular stresses, we can then input them into other fatigue failure criterion. Of course, we've got Goodman, which we've already seen, and now it looks a little bit simpler, right? But we can also apply it to things like Morrow or Gerber or Smith-Watson-Topper and be able to determine the shaft diameter that gives us infinite life for a particular set of loading conditions, or to determine what is the safety factor given those loading conditions and a known diameter of our structure. So overall, in terms of designing shafts, we have quite a bit of work to do in finding those moments and shear forces calculating those modular stresses, and then evaluating them against a fatigue failure criterion to figure out what survives to infinite life. Now, beyond infinite life, which is the lower band, we also need to consider the case of yielding. If the stresses are large enough for our structure to yield, then the stress life approach to fatigue does not work. We need something local. We need something like the strain life approach. And so we also need to check for yielding. How do we do that? Instead of looking at the amplitude or the mean stress, we calculate von Mises stress in terms of the maximum stress applied to our geometry. It can simply be the max stress if we know it, or it can be the mean plus the amplitude, which is going to give us the max. When we put that together into von Mises equation, we end up with this pretty complex term that includes the diameter of our shaft and the moments and torques that are applied to it. And then from this, we can then find the safety factor for yielding, where the yield strength of our material divided by the von Mises stress calculated in terms of max gives us our safety against first cycle yielding. Now, in some problems, we may not have directly the value of the maximum stress. We may be told that the amplitude is this and the mean is that. And so alternatively, if we don't know the max exactly, we can say that it's approximately the von Mises amplitude plus the von Mises mean stress within our structure. Now finally, very finally, is the simplification of rotating shafts. If we have a shaft and it is subject to both constant or steady bending stresses, so we have some forces that induce bending in our structure, and we have a constant or steady torsional shear stress to our shaft while it is bending, we will have the following states of stress. The bending mode, if it is a rotating shaft, will be completely reversed, meaning as the shaft rotates, every portion on the outer surface of this shaft is going to go through equal parts tension and compression. And so we will have a case where the max and the min value of fatigue stresses are equal, and the mean stress, the normal mean stress, is 0, right? Similarly, or actually not similar, but differently, if we have a constant torque or steady torque applied to a shaft under constant load, that torsional stress is going to be steady, meaning that as the shaft rotates, we will not have a torsional shear stress that increases or decreases across the structure. Rather, we will have a constant mean value, a mean constant value of torsional shear stress throughout that cycles to failure. So in this case, if we were to consider a rotating shaft, the previous equations simplify, where the mean moment and the amplitude of the torque are equal to 0 for this specific condition. And this can dramatically simplify problem solving for rotating shafts. Now, overall, there's a lot of work that we have to do for shafts. We have to find the endurance limit, the modified endurance limit. We have to figure out what is the state of stress applied to our shaft. If our shaft is rotating, we have to figure out how that rotation of the shaft gives us different types of fatigue stresses. And then overall, we have to plug those stresses in order to find the von Mises stress from which we can apply a fatigue failure criterion and determine the cycles to failure. So shaft design can be pretty complicated. But with enough practice, with enough careful thought to how stresses are evolving within our shafts, we can accurately predict if we have infinite life, if we have finite life and what the cycles of failures are, or if we have yielding in our shaft structure. And with that, this is the final video of machine elements.